Welcome back to another class with Ming. Today we talk about binomial theorem, and here are our learning targets. And we will start by considering these numbers in the expansions. Return. I hope that you have made these following observations. That is, 1. For the expansion of a plus b to the power of n, when n is a positive integer, that we see that, well, and when n equal to 0, I have 1 term. When n equal to 1, I have 2 terms. N equal to 2, I have 3 terms in the expansion. N equal to 3, I have 1, 2, 3, 4 terms in the expansion. Therefore, I can make the conclusion that the number of terms is always going to be the number of the index n plus 1. So n plus 1 terms. Continuing with that, I can make another observation that if I pay attention to the index of the terms here, all of them are power 1, a to the power of 1, b to the power of 1. Here, when it's n equal to 2, here is a to the power of 2, here's a to the power of 1 and b to the power of 1, but 1 plus 1 is 2, so the sum of the indices is actually 2. Here is actually 2. When n equal to 3, 3, 2 plus 1 is 3, 1 plus 2 is 3, and here's 3. So I can say that the sum of the indices of all the variables a, b must be equal to the number of n. You should be able to recognize that the 2 here, a to the power of 2, next is a to the power of 1. Here's no a. Or you can think of it as a to the power of 0, for example. And here, the same, a to the power of 3, a to the power of 2, a to the power of 1, a to the power of 0. Well, b to the power of 0, b to the power of 1, b to the power of 2, b to the power of 0, b to the power of 1, b to the power of 2, b to the power of 3. Therefore, I can make this conclusion. That is, the index of the first entry, a, decreases from n to 0. Whereas the index of the second entry, b, increases from 0 to n. Okay. Last is that if you look at the coefficients in front, here's a. You can think of it a 1, 1. Here's 1, 2, 1. And here's 1, 3, 3, 1. Do you recognize what these numbers are? Very good. So for people who have seen this before, you will recognize that these are the entries or the entries in the Pascal triangle. Well, in China, this will be called the Yang-Hui's triangle. Well, with this observation in mind, let's see how we can use this observation to help us to do questions like this. For example, if you want to expand a plus b to the power of 4, then what should we do? Well, we know that in this case we should have 5 terms. And a here, right, ab, first will be a to the power of 4, b to the power of 0, then a cubed b1, then a square b square plus a1 b cubed plus a0 b to the power of 4. Make sure that all of the sum is equal to 4. Then I put in the numbers from the Pascal coefficient. In this case is 14641, 14641, 14641. I can simplify this as a to the power of 4 plus 4a cubed b plus 6a squared b squared plus 4a b cubed plus b to the power of 4. We'll do the similar process. So we start with a to the power of 5 b0 plus a to the power of 4 b1 plus a cubed b squared plus a square b cubed plus a b to the power of 4 plus a0 b to the power of 5. and the coefficients are 1, 5, 1, 5, 10, 10, 5, 1. So I'm going to put that in 1, 5, 10, 10, 5, 1. So simplifying it will be a to the power 5 and so here's the answer.